we continue the lecture number 6 with linear transformation, and that is very important thing. That part of the lecture number 6 saying that any linear transformation can be represented in the form of the matrix. Means if you look at the screen here, a linear transformation T can be given first by a formula like that. Is very familiar too. But however, we can give it in the form, in the matrix form like that one. And in the lecture class last Wednesday, I explained to you the advantage of the matrix form is that it is shorter for you to write, usually because we write just only like that one, and also it is shorter to read, and more most important thing that is it is more convenient to integrate it into an algorithm in the computer to do the calculation. So that is an advantage of the matrix form of a linear transformation. And how we can represent any linear transformation in the matrix form, it is here. First, we consider only the linear transformation T from n space Rn into M space Rn, and that will lead to the notion of standard matrix. And because for n space Rn or Rm, we always have the standard basis denoted by E1, E2, En. That depends on the dimension of the domain and codomain here, n or m here. Then first we calculate T of E1, T of E2, T of En. That is n vector in the standard basis of the domain. And then we write down the coordinate of TE1, TE2, TEN. We write the column, coordinate column like that. And we put those columns side by side like that one. You get a matrix A. And that matrix A will be called the standard matrix for the linear transformation T. And more than that, the matrix A satisfy that formula. It means that T of V now can be obtained by multiply the matrix A and the coordinate column V. Yeah. That is satisfied for any vector V inside Rn. And the examples with the very simple one, that is standard matrix for zero transformation from Rn into Rn is always m by n zero matrix. And also the standard matrix for the identity transformation from Rn into Rn is identity matrix of the order n. And then next we study the composition of two mapping. Suppose that we are given two mapping, T1 from Rn into Rm and T2 from Rm into Rp. Then we can get the so-called composition of T1 and T2. It is by formula, it is given by that, or by notation we write T equal T2 composed to T1. And how we can define it? It is very easy for, at least for me, but I believe that is for you. You look at the, it's easy if you look at the illustration here. Suppose that we are given a vector V inside the domain Rn, the domain of T1. So first we use T1 to send it into W. That is in the codomain of T1. But codomain of T1 is a domain of T2. So then we can use T2 to continue to send W to U here. So if you go from V to first to W, then to U, first by T1 and then by T2, you get a mapping from here to Z, and it is denoted by T and we call it the composition of T1 and T2. And then in case both T1 and T2 they are linear transformation, we have the following observation. If T1 and T2 both of them are linear transformation, then the composition T like that is again a linear transformation. And more than that, if standard matrix of T1 is A1, of T2 is A2, then the standard matrix A of T will be the matrix product A equal A2 multiplied by A1. And please pay attention to that is the order of when you write A2 and A1. A2 go first and then to A1. It is the same like you write here T equal T2 composed to T1. Yeah. That is a very, very important thing. Otherwise, you can make the mistake. Then we define the notion of inverse of a linear transformation. Now we consider the case when T1 going from Rn into Rn. Just only the domain and codomain are the same. So we have a T1 and T2. Both of them are linear transformation from Rn into Rn. If T1 and T2 satisfying two equality like that for any vector v inside I, we say that T2 is inverse of T1. And in that case, we say T1 is invertible. T1 is invertible, khả nghịch. And because if the transformation T is invertible, then the inverse means the T2 satisfying that is unique. We can find only one linear transformation T2 satisfying that. Then the inverse of T will be denoted by T to the power minus 1. Then we have the following claim. Suppose that T from Rn into Rn is a linear transformation and it has standard matrix A. Then we have a following equivalent claim. The first one saying T is invertible. The second one saying T is an isomorphism. And the third one saying that the matrix A is invertible. So if you look only at the first and the third one, you will see that a linear transformation T from Rn into Rn is invertible transformation if and only if its standard matrix A is an invertible matrix. And more than that, in case T is invertible with standard matrix A, then the inverse of T will has standard matrix A inverse. And then that is a standard matrix for a linear transformation from Rn into Rn. Now we consider the general case. It means that we consider a linear transformation T from any vector space V into any other vector space W. And suppose that we have a basis B for the domain V and we have a basis B prime for the codomain W. And suppose that B consists of V1, V2 up to Vn. Then first we calculate T of V1, T of V2, and T of Vn. Those vectors lies in the codomain W, and W has a basis B prime. So we can write down the coordinate column of TV1 relative to the basis B prime, and we get the column here. Similarly, for T of V2, the coordinate columns relative to the basis B prime will be here. So we get n column and we put them side by side. You get a matrix A again, denoted again by A. It is here. And we call it the matrix of the linear transformation T relative to the basis B and B prime. And more than that, A will satisfy that formula. And there is one thing you should pay attention to. On the left-hand side, the left-hand side of the equality here, that is a coordinate of T, V relative to the basis B prime. But on the right-hand side, V here is a coordinate column of the vector V, but relative to the basis B. And you see, on the domain, we have the basis B, and on the codomain, we have basis B prime. That is the reason why we need to say that matrix of T relative to basis B and B prime. So we summarize it here. T from V to W is a linear transformation, and B is a basis for domain. B prime is a basis for the codomain. The matrix of T is defined like that, and we call it the matrix of T relative to the basis B and B prime. And A satisfies the equality here. And we can compare it with the standard matrix. In the formula for standard matrix is almost the same like the formula in the general case. The only difference is that in the general case, we need to specify the coordinate in which basis. Here's it. Coordinate relative to the basis B prime and coordinate relative to the basis B. And here we don't need to specify the basis, because here on domain and codomain we always choose the standard basis, and that is a fixed already. Now we consider the special case. Special case when domain and codomain are the same, and on both sides, on domain and codomain, we choose the same basis B. Then in that case, the matrix A will become the matrix of T relative to the basis B. Now we need only to specify only one basis, not two basis B and B prime as before. And in particular, in case T from V to V is identity transformation, and I will not repeat the definition of identity transformation here. But however, T is identity and B is any basis for V. Then the matrix of T of the identity transformation relative to any basis B is always the identity matrix of order n. It is here. So that is a remark we know already from last week. And finally, we study transition matrix and the notion of similarity. Now, suppose that we are given a linear transformation T from V into V. That is the case when domain and codomain are the same. It is given by a formula. V is sent to T of V, like that. Now suppose that we have two different bases B and B prime on the space V here. V1, V2, Vn, and B prime W1, W2 up to Wn. That is two different bases for V. A. Suppose that matrix of T relative to B is denoted by A. It is defined like that. And matrix of T relative to B prime is defined by that formula. So what we are doing in this slide we know that A and A prime, they are two matrices of the same linear transformation, just only relative to two different bases B and B prime. So we want to know how A and A prime are related to each other. What is the relation between A and A prime? And it is defined as follows. First, because we have two different bases B and B prime, then we have a transition matrix. The transition matrix from B prime to B is defined like that, and transition matrix from B to B prime is defined like that one. And whenever we are given A prime, B, P inverse here, we have the following equality that we studied already several weeks ago. Now, A and A prime is related to each other by that formula. The formula, the relation between A prime and A is here. And P, here P is transition matrix from B prime to B. And how we can get it? That is because if we go from here to Z, you have two ways to go. The first one, you go the direct way. The direct way means we send the coordinate of V relative to the basis B prime to the coordinate column of TV relative to the basis B prime. And the other way is we call it the indirect way. So first we go from V, we change the coordinate of V relative to B prime into V, but now the coordinate relative to the basis B, not B prime like down here. And then we use the transformation T, we send it into T of V. Here we have a coordinate column of TV relative to the basis B. And then once again, we change from the coordinate column of TV relative to B back to the coordinate column of TV relative to the basis B prime. So that is an indirect way. And both sides give the same reason here. That is why we have get A prime equal P inverse A P. And that formula gives us a new notion, that is similarity. Oh, sorry. Here. Then two square matrices A and A prime of the same order will become similar to each other if we can find an invertible matrix P so that A prime equal P inverse A P. So that formula is exactly the same like here. A and A prime similar to each other. And because of that, we see that two matrices A and A prime of the same linear transformation, but now relative to two different bases are always similar to each other. That is the reason of the previous slide. And at the end of the lecture number 6, I claim for you some advantage of the diagonal matrices. Suppose that D is a diagonal matrix with the entry on the main diagonal like that. Then D to the power K will be that one. And D, if you take transpose, nothing change. And if it, in case on entry are non-zero, then the matrix D will be invertible. And D inverse will be that one. 1 over D1, 1 over D2, up to 1 over Dn. And then after that, we continue with the lecture number 7. Lecture number 7 deal with the title is Eigenvalue and Eigenvectors. But however, the main ingredient of lecture number 7, that is about the diagonalization of a square matrix and of a linear transformation. But however, last Wednesday, we first repeat the notion of eigenvalue and eigenvector. It is here. Suppose that we are given a square matrix of order n, and you are required to determine if there exists a non-zero vector x in Rn, so that A multiplied by coordinate column of x will be multiple time of x, or you can formulate it in the mathematical formula like that. A is a square matrix of order n. Lambda is a number. X is a non-zero vector in Rn. If we have the following equality, then the number lambda will be called eigenvalue of A. The vector x will be called eigenvector of A corresponding to eigenvalue lambda. There is one important thing, that is x must be non-zero. And here is an example. If you have A like that, and x1 and x2 to be like that one, and you see x1 and x2 here is exactly the vector of standard basis for R2. Then you multiply A to x1, you get that thing. Then because of that, the number 2 here is the eigenvalue, and that vector x1 here is eigenvector corresponding to the eigenvalue 2. Next, we consider A to multiply by x2. You get x2, you get that one. It equals -1 x2. So it means that the -1 is an eigenvalue of A, and x2 like that is an eigenvector corresponding to the eigenvalue -1. That is an example. Then after that, we have the notion of eigenspace. Now suppose that A is a square matrix of order n. And suppose that we know already that lambda is an eigenvalue of A. Then the set of all eigenvector of lambda, all eigenvector corresponding to lambda, together with the zero vector, that will be subspace of Rn. And that subspace will be called the eigenspace of lambda. It will be called the eigenspace of lambda. There is one thing I would like to tell you at this point, that is together with zero vector. Why we need that? Because by definition, all eigenvector must be non-zero. Then we need to add zero vector inside that to make a subspace. Because you remember that any subspace need to contain zero vector. So we need to have it here. And here I summarize to you how we can find eigenvalue and eigenvector of a square matrix A. Suppose that we are given A, then an eigenvalue of A must be a number lambda satisfying that equation. That equation has name characteristic equation of A. And the eigenvector of A corresponding to eigenvalue lambda must be the non-zero solutions of the homogeneous system of linear equation lambda I minus A x equals 0. And if you look at the characteristic equation of A, the left-hand side here is a polynomial in variable lambda, and it has order, it has a degree n. The degree n is exactly the order of the matrix A, and that polynomial has name characteristic polynomial of A. So That is on what we studied last week. And now today we continue from this point. Now, suppose that we are given a matrix A like that. You need to find eigenvalue and eigenspace of A. Now we need to find eigenvalue. We know already. But now not only to find the eigenvector, we need to find the eigenspace. And it is here. We do as follows. If we are given a vector V with the coordinate x and y, then A multiplied by V, you will get minus x and y. And if you consider a vector lying on the x-axis, in the horizontal axis like that, that vector will have the coordinate x and 0, because the horizontal coordinate is always 0. Then if we multiply that with x0, you get minus x0. It means that equals minus 1 x0. So because of that, the number minus 1 will be an eigenvalue of A, and that will be an eigenvector. Any vector lying on the x-axis will be eigenvector, except the case when x is 0, because at that time the vector will become 0, and 0 is not an eigenvector. Similarly, if you consider a vector lying on the vertical axis, that is on the y-axis like that, it will have coordinate 0, 1. And if you multiply the matrix A to that, nothing change. You get again 0, 1. Or like we can write like that. It means that the number 1 is another eigenvalue of A. And that vector will be an eigenvector of A corresponding to lambda equal 1, except the case when y is 0, because at that time the vector will become the 0 vector, and 0 vector cannot be an eigenvector. Or if you want to look at the geometry, when you multiply a vector x, y with the matrix A like that, you will get the following. That will have a reflection by the y-axis, means we take the point from here to Z. Đối xứng qua trục tung. Reflection in the y-axis. Then, because of our investigation here, you see that the eigenspace corresponding to lambda equal minus 1 is x-axis on vector lying here. And the eigenspace corresponding to lambda equal 1 is y-axis here. And it is obviously the subspace of R2. And here is, I explained to you already, that is a way to find eigenvalue and eigenvector of any n by n matrix. Now, once again, we consider another example. A to be like that. And you need to find eigenvalue and eigenvector. So we write down the characteristic equation. It is here. And easily to see that it will have an eigenvalue minus 1 and minus 2. That is, eigenvalue is minus 1 and minus 2. For minus 1, in order to find the eigenvector, we need to solve the system, homogeneous system of linear equation. It is here. And the matrix here is row equivalent to that matrix. And that matrix, if you, once again, I call your attention to the way to solve the system of homogeneous system of linear equation. We need to look at the column containing the leading one. Here we have only one leading one here. Then the second column will correspond to free variable. It means that x2 can be given any value, and here I put it t. With that, you will find x1 must be 4t, or otherwise the solution will be t multiplied by the vector 4, 1, like that. And because the eigenvector must be non-zero, so we require that t is non-zero. For the second eigenvalue, -2, then once again, to find the eigenvector corresponding to -2, you consider the homogeneous system of linear equation like that, and we need to find non-zero solution. And by the same way, you will get the solution like that, t time of c1. And because we are looking for the non-zero solution, we require that t is non-zero. So that is on. That's on thing. Now, again, if we are required to find eigenvalue and eigenvector for the matrix A like that, is in next few slides you will see that it is very easy to find the eigenvalue for something here. But however, here first, the characteristic equation will be like that, and that equation has only one solution, that is lambda equal 2. So it means that we have only one eigenvalue, lambda equal 2. But however, if you look at the equation here, the solution lambda equal 2 is counted c time. Nghiệm lambda bằng 2 được tính 3 lần ở đây. Ở đây chúng ta có lambda trừ 2 mũ 3. So that is something new for you here. Now we are looking for the eigenspace of A corresponding to lambda equal 2. Okay, the homogeneous system of linear equation to be that we are looking for the non-zero first, to the non-zero solution, and we solve it by using Gauss-Jordan elimination to get that one. And from here you see that that column and that columns are free. It means that the first and the second, first and the third variable can be any value, and here I give it s and t, and then you can solve it. You get x2 must be 0 for in any case. So our solution will be s time of that plus t time of that. And because we are looking for the eigenvector, so we require that st is non-zero. St is non-zero. And also, those vectors are linearly independent, so the eigenspace of A corresponding to lambda equal to will be something like that. Will be like that for any s and any t in the real number. When s equal t equal 0, that is 0 vector, and we add 0 vector to the set of all eigenvector, we get the eigenspace of A corresponding to lambda equal 2. So it is here. So that is the way the example give you explain to you how you can find the eigenspace of a vector corresponding to some eigenvalue. And because we have that is basis, so the dimension of the eigenspace is 2 because the basis consisting of 2 vectors. Now I going back to the previous slide. An eigenvalue lambda, if it appears as a multiple solution, multiple root k time, we will call it, we will say that the lambda has multiplicity k, multiple root. In Vietnamese we say nghiệm bội. If lambda 1 is a nghiệm bội of characteristic polynomial, if it is k time, then we say lambda 1 has multiplicity k. Khi đó ta sẽ nói lambda, cái eigenvalue lambda này sẽ có bội bằng k. And that is our example here. Here, the eigenvalue lambda equal to here has a multiplicity 3 here. Why that? Because that solution for polynomial, for a characteristic polynomial, is counted 3 times. Here you have lambda minus 2 multiplied by lambda minus 2 multiplied by lambda minus 2. It means that the number 2 is counted 3 times. So then the observation, we have an observation saying the multiplicity of an eigenvalue is greater than or equals the dimension of its eigenspace. And we can see it by previous example. And here we know already that the eigenvalue lambda has a multiplicity 3. Lambda bằng 2 có bội 3. But however, the eigenspace of A will have a dimension 2. Dimension 2. It means that the multiplicity of lambda is more than, is bigger than that one. So that is what we write it here. Okay, next. Now you are required to find the eigenvalue of the matrix A like that. And you need to find a basis for each of the corresponding eigenspace. So now, more than to find the eigenvector, you need to find eigenspace. And for each eigenspace, you need to find a basis. But however, we have many things, but we should do it step by step. You will see it is not so complicated. First, the characteristic equation to be that, and it's that, it's very easy to see that A will have the following eigenvalue: 1, 2, and 3. 2 and 3 will be eigenvalue with multiplicity 1. But 1 will be eigenvalue with multiplicity 2. So now we have 3 different eigenvalue, or if you count with the multiplicity, you have 4 eigenvalue. And here we say eigenvalue to be like that. Next, for the first one, lambda 1 equal 1. In order to find the eigenvector or an eigenspace with corresponding to lambda equal 1, you write down the homogeneous system of linear equation like that. You get that one. Using elimination to solve it, we get that one. Then our solution will be S of z vector plus T of z vector. Here I will not repeat once again about how to solve a homogeneous system of linear equation. I write down immediately that the solution to be that one. And because we require, first we want to find the eigenvector, so we require ST is non-zero. Then those two vectors are linearly independent, so it makes a basis for the eigenspace of A corresponding to lambda equal 1. That is the first thing. The second eigenvalue lambda equal 2. Then again, looking at the homogeneous system of linear equation, we get that one. And solving that, you get the solution like that t time of that vector. And because eigenvector must be non-zero, so we require t is non-zero. However, if you consider the eigenspace, then that one vector is a basis for the eigenspace, or in other words, eigenspace of A corresponding to lambda equal to has dimension 1. Last, for the eigenvalue 3, then again the system to be that and the solution to be that. Again, we require t is non-zero, and the eigenspace will be generated or will be spanned by that vector, means it has dimension 1. Now we consider the case of triangular matrix. If A is a triangular square matrix, then on the eigenvalues are the entry lying on the main diagonal. You can see it by looking the following examples. We have A and B like that. A is a lower triangular matrix, and B here is even B here is a diagonal matrix. Now we can consider only the case A. Then determinant of lambda I minus A will be determinant of that matrix. That matrix is still a diagonal matrix with entry like that. Then its dependent equals the product of all entry lying on the main diagonal. So we get that one. And that, if we write down the characteristic equation, you will get the solution. Lambda 1 equal 2, lambda 2 equal 1, and lambda 3 equal minus 3. So we have a 3 different eigenvalue. The second case, it is very easy for you to verify, so I will not write down the calculation here. Next, we define the eigenvalue and eigenvector for any linear transformation. We know already that if we are given a linear transformation T from V to V, it can always be represented by a square matrix A. First, we fix a basis B on both sides. Then T can be given by a matrix A. And because of that, we can imitate the notion of eigenvalue lambda and eigenvector X of the matrix A, here. And we borrow it and we define similar things for any linear transformation T. It can be done as follows. A number lambda will be called an eigenvector of linear transformation T from V to V if we can find a non-zero vector X of V so that T of X equal lambda time of x. In that case, x will be called an eigenvector of t corresponding to the eigenvalue lambda. And also, the set of all eigenvector corresponding to lambda together with the zero vector will be a subspace, and we call it the eigenspace of eigenvalue lambda. So that is the notion of eigenvalue and eigenvector of any linear transformation. And the example is here. Now we consider the linear transformation T from RC into RC by the following, by that formula. And you are required to find its eigenvalue and eigenvector. How we can do it? Of course, we do as follow. We find its standard matrix, and in order to find its standard matrix, you can do as follow. You calculate TE1, TE2, TE3, and then we write down the coordinate column. But however, I explained to you last Wednesday already that you can look at the expression here and you can find it. Okay. 1 C0, C10 and 00 minus 2. You can going back here. 1, 3, and 0 because there is no H3 in this here. And the next one 3, 1, 0. And the last one will be 0, 0, minus 2. So it is here. Now we have already the standard matrix is here. Then the characteristic equation will be like that one. So we have two eigenvalue. Lambda 1 equal 4 and lambda 2 equal minus 2. And lambda 2 has multiplicity 2. It means that lambda 2 is counted twice. And I omit, I skip the calculation to find the basis for the eigenspace. And I say that for lambda 1 equal 4, we have a basis of eigenspace consisting of only one vector. But for the lambda equal 2, for the eigenvalue equal minus 2, we have a basis for eigenspace consisting of two vectors like that. And see those vectors are linearly independent. I claim that you can verify it by yourself. So let T from RC into RC is be the linear transformation having standard matrix as in the previous thing. And if you consider the B prime, the new basis for RC consists of three linearly independent eigenvectors we found in the previous slide. Then A prime, the matrix of T relative to the basis B prime, will be diagonal. More precisely, now we denote B prime to be the basis consisting of three eigenvectors we find in the previous slide. Then the matrix A prime of T relative to this basis B prime will be that one. And there is one more thing you should pay attention to. Here is already the eigenvector of A, but here on the right hand side, on the entry now lying on the main diagonal, they are eigenvalue of A. We are going to study that by the end of today, but now just only you need to pay attention to. If you choose a new basis consists of all linearly independent eigenvector, then the A prime, I mean the matrix of T relative to the new basis will be that thing. the main diagonal entry of A prime as the eigenvalue of A. And so we are going to came into the part about the diagonalization, but we do it after the break. So we should have a break now, please. So let's continue the class now. Are you coming back?
Yep.
Okay.
Yes.
Okay, so let's continue now. We continue with the problem about the diagonalization. So before the break, we consider an examples, and the examples give us the following observation. In case we choose a basis consisting of on the eigenvector, then the matrix of the linear transformation will be in the diagonal form. And more than that, on the entry lying on the main diagonal will be the eigenvalue, of the matrix A. Then with that, we are going into the section about the diagonalization. So what is the diagonalization? So we suppose that you are given a square matrix A, and you are required to determine if there exists an invertible matrix P, so that P inverse multiplied by A multiplied by P will be a diagonal matrix. And if such an invertible matrix P exists, it means that if we can find an invertible matrix P, so that P inverse AP is a diagonal matrix, then A will be diagonalizable. And we say, another one, we say that the matrix P diagonalize the matrix A. Or in Vietnamese, we say matrix A là chéo hóa được, matrix P là chéo hóa cái matrix A. So that is the terminology in Vietnamese. And now I repeat to you the notion of the similarity. Two matrices A and B, square matrices of the same order, will be called similar to each other if we can find an invertible matrix P, so that B equal P inverse multiplied by A multiplied by B. So we will look at here, it is quite similar to Z. So the eigenvalue problem, or the eigenvalue problem is and the similarity notion is related closely to the diagonalization problem here. We are going to see it in the next slide. Now, suppose that A and B, they are similar matrices of the order n. Then we'll see that they will have the same eigenvalue. They will have the same eigenvalue. Why is that? Suppose that A and B are similar. It means that B equal P inverse A P. and P is some invertible matrix, square matrix. Then you need to remember some property of matrix operation. You can calculate the determinant of lambda I minus B, and it equals the determinant of lambda I minus A. It means that A and B, they have the same characteristic polynomial. It means that they have the same characteristic equation. Then it has the same eigenvalue. So that is the reason why you see A and B are similar, then they will have the same eigenvalue. On the calculation here, you can read and you can verify in the slide I put on the button. And here is some example. We consider the matrix A like that, and the characteristic equation will be something like that. Will be something like that. With that, you will have eigenvalue 4, -2, and -2. Now you see here, the -2 is one solution of the characteristic equation, but however, it is counted 2 times. So because of that, it is written like that, -2 and -2. And for lambda equal 4, you get the eigenvector like that one. And for the eigenvector P2, for eigenvalue -2, you find two eigenvector P2 to be that and P3 to be that. That we did already in the previous example number 5. Then we put them together. We put them side by side, the 3 eigenvector P1, P2, and P3. And we write it in the column, and we put the column side by side. We get a matrix P. And because P1, P2, and P3, they are linearly independent, so the matrix P will be invertible. And you can verify that P inverse multiplied by A multiplied by P equals the diagonal matrix like that. And the entry lying on the main diagonal are eigenvalue of A. And I put a remark here for you. Here you put P1, P2, P3. Then the eigenvalue appear on the diagonal of that will be like that. But if you put the second column to the first column, and the first column now into the second column, then the diagonal matrix now will become like that. Then it means that the order of the eigenvalue appear in the diagonal here depends on the order we put the eigenvector on there. And once again, if here you write P2, P3, and P1, then the eigenvalue will be order like that on the diagonal. Thứ tự các cái giá trị riêng nằm ở trên đường chéo khi mà ma trận đã về dạng đường chéo, nó phụ thuộc vào cái thứ tự mà chúng ta đặt các cái vector riêng ở đây vào cái cột đây. Cột thứ nhất thì sẽ ở bên này sẽ tương ứng với vector với giá trị riêng thứ nhất, cột thứ hai sẽ ứng với giá trị riêng thứ hai, cột thứ ba ứng với giá trị thứ ba. Nếu chúng ta đổi chỗ thì lập tức các cái cột này sẽ đổi cho nhau, nhưng lúc bấy giờ thì thằng này nó sẽ lên trên, còn thằng này nó sẽ xuống dưới. So, that is the reason, that is what I say a remark here for you. So usually, in order to see if a matrix A is diagonalizable or not, it requires you to do a lot of calculation. But however, we have a criteria to see if a matrix A is diagonalizable or not. It is here. A will be diagonalizable if and only if it has n linearly independent eigenvector. So that is, we have n linearly independent eigenvector, and n is exactly the order of the square matrix A. And it is explained in the slide on the model, so I will not repeat it here, but it is explained very in the detail on the model. So I leave it for you to read by yourself. In case, the last one, in case we cannot find n linearly independent eigenvector, so the matrix A is not diagonalizable. So there is one thing I forgot to write here. That is, in case you cannot find n linearly independent eigenvector, here I forgot the word eigenvector. If we cannot find n linearly independent eigenvector, then the matrix A is not diagonalizable. And here is a example for you. Now you are given a very small size matrix A of size 2 by 2, like that. Then the characteristic equation to be that, so we get the eigenvalue lambda 1 equal 1. It is counted 2 times, or we say it has a multiplicity 2. But however, in order to find eigenvector, for that you get only one vector. You cannot find two linearly independent vector, eigenvector. So in that case, the matrix A is not diagonalizable, because we cannot find two linearly independent eigenvector for A. So A is not diagonalizable. I summarize for you. Suppose that you are given an n by n square matrix. You are required to diagonalize it. How you can do it? It can be done in 3 steps. On calculation will be contained in the first step. That is, you need to find n linearly independent eigenvector P1, P2, Pn. And that will corresponding to eigenvalue lambda 1, lambda 2 to lambda n. That is what you need to find. The next step will be, so whenever you find already n linearly independent eigenvector in the first step, all you have to do in the second step, that is, you put them side by side in the column, like that. You get a matrix P. And because those vectors are linearly independent, so you know that P is invertible. And then the last step, you write P inverse multiplied by A multiplied by P equals the diagonal matrix, and you put the eigenvalue lambda 1, lambda 2, lambda n on the diagonal. So please pay attention to the order you put P1, P2, Pn here. So that with that, the order of lambda 1, lambda 2, lambda n will be here. So you should remember that you don't need to find the P inverse. No, you don't have to find the inverse of the matrix P, because you know exactly that must be the diagonal form, and on the entry on the diagonal will be the eigenvalue you found already in the first step. So that is the reason why I say that on calculation appear in the first step, and second step and last step is only write down. And the only thing here, that is, you need to pay attention to the order of the vector you put in the P, and the order of eigenvalue you put on the diagonal here. So that's it. You have 3 steps. And once again, I put the remark here, the order of eigenvalue to form the sorry, here is once again I made a mistake. The order of the eigenvector I put in the matrix P will determine the order of eigenvalue appear in the main diagonal of D here. Now we look at the matrix A like that, and you are required to find a matrix P so that P inverse AP is diagonal. How you can do it? It is here. First, you need to write down the characteristic equation. It is here. With that, you get C eigenvalue 2, -2, and 3. Then for lambda equal 2, you get that thing. To find the eigenvector, you need to consider the homogeneous system of linear equation. And I will not repeat the way you solve a system of linear equation. And you get that one. The solution will be that. And in order to get the eigenvector, you need T must be non-zero. And here I choose T to be 1. So I get the vector P1 to be that. For lambda equal -2, we do the same way like that. You get nothing. And you get an eigenvector to be P2 with the coordinate like that one. And the last one with the eigenvalue 3 like that. And you will get the eigenvector to be that one. Now you put them side by side. You put them side by side, P1, P2, P3. You get the matrix like that. And you know immediately that P inverse multiplied by A multiplied by P to be that one. And the order of eigenvalue here is exactly the order P1, P2, P3 we write in the matrix P here. And next, I explain to you. That is what I explained already by the end of the lecture number 6. That is the advantage of the diagonal matrix. Suppose that D is a diagonal matrix, then D to the power K will be like that. Here K is a positive integer. K là một số nguyên dương. We take the power of D, we get that one. Then we can use that in the following way. Suppose that you are, no, first, please don't look at here. I explain to you. The last one only, the last line here. Suppose that you are given a matrix A, a square matrix A, and you are required to find A to the power K. In some exercise, I can give you the K is something is very big one. K something like 2021. Là có thể cho K bằng 2021. That is this year. How you can find it? In case A is any square matrix, it is very difficult because it is not so easy for you to multiply matrix to matrix and you do it cây time. But however, you can do as follow. First, you diagonalize it. Chúng ta chéo hóa cái ông A này trước. Then, by diagonalize A, we get the following. We can find P so that P inverse multiplied by A multiplied by P equal D. That is a diagonal. Now we use that. You see that D to the power K, we know how to find it here. But on the right hand side, if you take that to the power K, you will get here some calculation, and finally you get P inverse multiplied by A to the power k and multiply by p. Or from here, we get a to the power k equal p multiplied by d to the power k multiplied by p inverse. Now it is very easy because d to the power k is here. And p inverse you find in the first step here. So that is one way to find the power of a square matrix. That is the application of the diagonalization of the matrix. Then there is one more thing. Sometimes you are not required to diagonalize a matrix. You need only to know if a square matrix is diagonalizable or not. Đôi khi các bạn không cần phải chéo hóa hết một mã trận. Người ta chỉ hỏi các bạn xem cái mã trận này có chéo hóa được không. So here you have a criterion to verify if A is diagonalizable or not. That is, in case A has n eigenvalue and all eigenvalue are different from each other. I say, in case the square matrix A of order n has n distinct eigenvalue, then we know that A is diagonalizable. Then we say that A is diagonalizable. And here is an example. Suppose that you are given A to be a matrix like that, and you are required to see if A is diagonalizable or not. It is very easy. You don't need to do any calculation here. The first one, A is a triangular matrix, the upper triangular matrix. Then on of its eigenvalue will be the entry lying on the main diagonal. So we know that A will have eigenvalue 1, 0, and -3. And also because those eigenvalues are different from each other, then we say that A is diagonalizable. We don't need to do any calculation here. Next, we consider the program of diagonalize a linear transformation. So it is done as follows. Suppose that suppose that we have T from V to V is a linear transformation. Now we need to find a basis B of V so that the matrix of T relative to the basis B will be a diagonal matrix. And how you can do it? And it is here. You can see as an example number 7. Number 8. Now we consider again T from R3 into R3. It is a linear transformation given by the formula like that. Then you need to find a basis for R3 so that the matrix of T relative to B must be diagonal. How you can do it? We do as follows. For that, you can write down the standard matrix for T. The standard matrix is here. And now we continue with that to find the eigenvalue for A, eigenvalue and eigenvector. The eigenvalue will be 2, -2, and 3. That matrix is exactly the matrix in the example number 5 in the previous slide. Then we have 3 eigenvalue. And with that, you will get again eigenvector P1 is here. Second, will be those eigenvector here. And the last one will give us another eigenvector P3. So we have three eigenvector P1, P2, P3. They are linearly independent, and because of that, it must be a basis for R3. And because T of P1 equal to P1, T of P2 is minus 2 of P2, and T of P3 is C times of P3. So if we write down the coordinate column of that according to the basis B like that, the coordinate of TP1 will be 2, 0, 0. The coordinate of TP2 will be 0, minus 2, 0. And the last one will have the coordinate 0, 0, and 3. Now, if we put them side by side, you will get 2, 0, 0, 0, minus 2, 0, and 0, 0, 3. That is exactly the matrix of T relative to the basis B. It is here. It is already in the diagonal. Moreover, if you remember the matrix P we write in the previous slide, the matrix P consisting of that is exactly the transition matrix from the basis B to standard basis. So because of that, we integrate P inverse A P equal that one. So that is it. You can consider that is a formula for similar matrix, and that is exactly the definition of the matrix of T relative to the basis B. So you can go by two ways. The first one, we go by definition. The second one, you go by the diagonalization of a matrix A. Like that, you can choose which one you like. Next, we consider the symmetric matrix and orthogonal diagonalization. First, I would like to call you the notion of the symmetry. A square matrix A will be called symmetric if it equals its transpose. Means if A equals A transpose like that. Here is some example. A to be that, B to be that, and C to be that. Then you can verify which one is symmetric and which one is not. That one is symmetric. And also if you look at the form, you say it is symmetric by the main diagonal. If you turn it by diagonal, nothing change. The second one also is a symmetric, but the last one is not. It is a non-symmetric because if you take transpose, that entry will go here. But here is a 2 and here is a 1. So it is not the same. Then we have the following observation about the symmetric matrix. The first, now suppose that we are given n by n symmetric matrix. Then we have the following property. The first one, A, the matrix A is always diagonalizable. The symmetric is always diagonalizable. The second property is on eigenvalue of A must be real. At the moment, you can forget the property number 2. Why is that? Because usually we can consider the complex number. But however, in this case, in this course, we consider only the real number, so you can forget it. The next one, the next property. Suppose that lambda is an eigenvalue of A with multiplicity k. It means that lambda is a solution with a multiplicity k of characteristic equation. Then, in that case, the eigenspace of lambda will have the dimension exactly k, or in other words, we can say that lambda has exactly k linearly independent eigenvectors. That here is an example illustrate for you that now we consider the very easy case, that is the case of symmetric matrix of sign of order 2, like that, A, B, AC, and CB, like that. Then first we consider the characteristic equation of A. It will be like that. It's a polynomial of degree 2, đa thức bậc 2. Then you will have the following. The discriminant of that polynomial will be that one. I don't know, seems discriminant in Vietnamese is biệt thức or something. Biệt thức of the polynomial of degree 2. It equal that. And that is obviously is non-negative. Non-negative means that polynomial must have solution. We have two cases as follows. The first one, if the discriminant equals 0, it means that C equals 0 and A equals B. And when C is 0 already, then the matrix is already in the diagonal. Is already in the diagonal. We don't have to do diagonalization of A. And in other case, that the discriminant is positive. If the discriminant is positive, then the characteristic polynomial will have two different solutions. Because it has two different solutions, it means that A will have two different eigenvalue. And because of that, A will be diagonalizable. So that is some explanation for you that in case A is a symmetric, then in case A is a symmetric matrix, the dimension of the dimension of any eigen space equals the multiplicity of that eigenvalue. So that is some explanation for you. Next, that is a notion of orthogonal matrix, and we are going to climb into just a little more complicated notion, that is orthogonal diagonalization of a square matrix. But however, because it is somehow complicated and a little long, so I will leave it to the next week, and this week we will stop here. So the class today will stop here. And do you have any question about the class, about the lecture? Please. So if you don't have any questions, so we'll see each other next week.
Bye.